All right, so now let me briefly describe what I view to be the connections between information geometry and mechanics. As well as the connection then with mechanics and optimization, which you should think of as being closely related to learning. Okay, so if you recall the last time we alluded to this idea of a divergence function, so I will try to be a little bit more explicit about what I mean by a divergence function. Okay, so a divergence function that's denoted by D is a map from two copies of some manifold to the non-negative rails on a manifold. Let's call it M, right? Is a thrice differentiable function satisfying the following properties. Okay, the first of which is that the divergence function for any pair of points is greater than or equal to 0 for all x and y in M, and equality only holds if x is equal to y, right? So you have, well, it's actually an if and only if, so equality if and only if x is equal to y. So if x is equal to y, it's like the divergence is like all those 2 points which are the same point is 0, and conversely, if the divergence is 0, those 2 points are the same. Okay, so the second thing is that okay, I'm going to introduce some notation. D sub I means that I differentiate this divergence function with respect to the ith component of the first thing. So, all right, and all right, so actually, let me finish my thought. So dixx, which is the partial of d respect to xi at this point xx is equal to 0. All right, and the same thing is true for comma j. All right, so comma j is the derivative of d respect to the jth component of the second variable. Okay. At a point xx is also equal to 0, and this is true for all I and j. Okay. All right, the third thing is that the mixed partial derivative, the negative of di comma j. So what that is the second derivative of d respect to xi and yj, right? So again, evaluated along the diagonal is positive definite. Okay, and if again it's like you know something about Riemannian geometry, you're going to be thinking that this is the object which is going to give you the induced Riemannian metric, and that's indeed the case. Okay, and then finally, yeah, so that's the main thing. And as we sort of talked about before, divergence functions sort of act like pseudo-distance functions. That are not negative. Well, sort of they're non-negative, as you would expect with a distance function, but need not be symmetric. And if you recall, it's like we discussed an example, it's like of a divergence function, in particular the Bregman divergence, where you would not expect the thing to be symmetric. Okay, all right. So, so those are the axioms. It's like which a divergence function satisfies, and then the next thing is to talk about the differential geometric objects which are induced by this divergence function, and you already sort of have a hint as to the first one, which is this negative d I comma j term evaluated along the diagonal. That's going to be positive definite, and that's again a candidate for a Riemannian metric. Okay, and that's going to be indeed the case. Okay, so so the geometry induced by divergence functions. So a divergence function induces a Riemannian metric. And I wouldn't worry if you haven't seen notions like Riemannian metrics and things like that before, even the notion of a manifold. We will discuss this in greater detail as the course progresses. The main point is to just give you, again, a high-level overview of, it's like what are the main players in this problem and what the connections are, so that you have a sort of conceptual framework on which to build your knowledge. Okay, so anyway, so a divergence function induces a Riemannian metric. Let's call that G, and a pair of torsion-free dual connections. Let's call them gamma and gamma star. And Gij of x is going to be minus the divergence function differentiated with the I component of the first term and the j component of the second term evaluated along the diagonal. Okay, and then the connection coefficients for one of them, which has a triple of indices I, j, and k, all right, it's going to be minus dij k. So that means I differentiate, it's a triple derivative, right, with respect to xi, xj, and yk, right, and then evaluate it again along the diagonal. And as you might expect, the dual connection is the one where you differentiate with respect to 2 of the second slot and 1 of the first slot. Here I've differentiated 2 to the first slot, 1 to the second slot. Okay, so gamma star I j k of x is minus dk comma ij. Okay, and as I said before, well, that these things are torsion free, right? So gamma and gamma star are torsion free. Right, and are dual with respect to the induced metric. Which I have here. This is the induced metric. So, in particular, what do I mean by that? Right. If this pi and pi star are the associated parallel transports, then the inner product between between it's like two vectors is going to be equal to the power transport of the first vector with respect to the first connection and the respect to the dual connection for the second one. Right? So we had discussed this before. All right. So so what happens is that it turns out that these things can be thought of as perturbations. It's like of the Levi-Civita connection. So I will state that just briefly. And the reason why I want to introduce this is because I want to introduce an inverse problem in a little bit. Okay. So gamma I jk is going to be equal to gamma 0 ijk, and gamma 0 ijk is going to be Levi-Civita, all right, minus 1/2 t I jk, and this is what's called the skewness tensor. Okay, and then gamma star ijk, is going to be the Levi-Civita connection again, right, plus 1/2 the skewness tensor. Okay. So another way to sort of see it is that the skewness tensor is equal to gamma star ijk minus gamma ijk. Okay, all right. All right, so the point is that if you had something like this, then we can talk about the following inverse problem. Okay, and so let me sort of briefly state the inverse problem for you. So we know that given a divergence function, D, right, we induce metric G and a pair of dual connections. Gamma and gamma star, right? So the question is the following. If we have a metric G and a pair of dual connections, gamma and gamma star, can we find D that induces them? Right? So this is sort of the inverse problem. We already know one direction, the forward problem, right? Given the divergence function, I can compute a metric, I compute a pair of dual affine connections, right? If, on the other hand, I gave you a metric and a pair of dual affine connections, can I find a D which induces those things? And so the first statement, or the first observation, if you will, is that this D is not going to be unique, all right? So D is not unique. Such a D is not unique. And we refer to such divergence functions as canonical divergences. Okay. So, how do you, or what is one possible way of constructing a canonical divergence? Okay, so this is where I'm going to start connecting things to mechanics. So, it turns out that one can construct such a divergence function, a canonical divergence, by applying Hamilton-Jacobi theory for the following Lagrangian. Okay, so this Lagrangian depends on position and velocity, and it's given by 1/2 Gij Vi Vj. So this is like a kinetic energy term, right? It's 1/2 mv squared, basically, right? Plus 1/12 Tijk at Q contracted into Vi, Vj, Vk. Okay, and if you recall, it's like this skewness tensor is just the difference between the two connections. Okay, all right. So it turns out that if you applied Hamilton-Jacobi theory to this, you get what is called a generating function, right? So if you do this, we get a generating function. Which turns out to be one of these canonical divergences. Okay, so that's kind of interesting. On the one hand, it's like you're using techniques, it's like from Lagrangian Hamiltonian mechanics, right, to construct canonical divergence. But there is something which is sort of implicit in this, which bears repeating, right, which is that this is a generating function associated with some sort of Lagrangian. So this naturally raises the following question, which is that is there again some deeper connection that's like between divergence functions and mechanics, right? So in particular, if you know something about Hamilton-Jacobi theory, then you know that these generating functions are generators of the symplectic map, which maps some initial state to the current state of the Lagrangian and Hamiltonian system. Okay, so that's kind of interesting that you can think of divergence functions now as generating functions of Hamiltonian flows. Okay, and so that's where the connection to mechanics, and in particular discrete mechanics, comes into play, right? So what this is saying is that you can think of divergence functions as generating functions of symplectic maps okay, and then this in turn has connections with mechanics, with discrete mechanics. Okay, but let's just focus on this idea of generating functions of symplectic maps for now. Okay, so all right. So the basic idea is that if you had this d as a generating function, so if d is a generating function, so it's going to be actually what is called a type 1 generating function. Okay, then I can define a map right, let's call that phi, from the cotangent bundle of the manifold to itself, defined implicitly in the following way. Okay, so let me just put coordinates on this. Let's say this is q0, p0, position and momentum, right? q1, p1. Okay. So then the map is implicitly defined by these equations. So P0 is equal to negative the partial derivative of d respect to x. So let me call that Q0. Sorry. Q0, and this is evaluated in Q0, Q1. And then P1 is equal to partial respect to d, partial d respect to Q1 of Q0, Q1. Okay, so this implicitly defines for you a map from Q0, P0 to Q1, P1, given this generating function d, which depends on two copies of the manifold, which is exactly what our divergence function does. All right, so you can check that this map is symplectic, and it's, it's like, and good stuff like that. So, so where are we going with this? So we're going with this as the following. So there turns out to be an interesting theorem, which states the following, right? So more or less you can ask the following. So I guess the previous thing was also a theorem. So given a divergence function d, right, there is an induced Riemannian metric G, right? So you can ask the following. Okay, so that's one thing, right? And then if we consider 1 over h of dxy as a generating function, well, let me call that d q0, q1 as a generating function of a symplectic map, right? We can ask, well, maybe let's not call it a theorem, let me just sort of write it in words. Okay, so generated function, it is a proven result, but it's like the way we are discussing it is not really set up. It's like as a statement of a theorem. All right, so given the divergence function d, there's this induced Riemannian metric G, right? And so if you consider this 1 over h d q0, q1 as a generating function, right, is this a good approximation of the time h geodesic flow with respect to G? Okay, all right. So again, it's like if we had taken this 1 over hd thing, it's like to define a map from Q0, P0 to Q1, P1, you can ask to what extent that is approximating a flow, it's like by time h along a geodesic of this Riemannian metric G. Okay, and a geodesic is basically, again, some sort of generalization of this idea of straight line flows in a sort of in a flat space. Okay, all right. So that's sort of the question. It's like which naturally comes out of this, and it turns out that it is always consistent. So that basically means that if you do take this approach, it will give you at least a first order accurate approximation. So first order, at least first order accurate. And if D is a Bregman divergence, then it is second order accurate. So what is the take-home message here, right? So the take-home message here is that, for example, we were working with Fisher-Rao. It's like metrics and KL divergence. Okay, so as we recall the last time, KL divergence induces Fisher-Rao as the associated Riemannian metric. So say I wanted to do geodesic flow with respect to Fisher-Rao. Okay, so it turns out that if instead I were to think of KL divergence divided by H as a generating function of a symplectic map, then that's going to be a second order accurate, at least a second order accurate approximation of the Fisher-Rao geodesic flow. Okay, so that's kind of interesting that it allows you to connect, it's like divergence functions and it's like with the geodesics of it, and to really think of the divergence functions as defining for you a symplectic map using this notion, or thinking of it as a type 1 generating function. All right, so again, that's kind of, it's like a high-level view. It's like of where some of the interesting potential connections, it's like come into play. The other thing, it's like which shows up is that there are connections between mechanics and optimization along these lines, and taking advantage of divergence functions. And I'll describe that in the next lecture. So let me just stop here for now.